All right, everyone. So, welcome to the third video in the heat transfer lecture homework series. This time, what we're going to do is we're going to work a little bit more with that problem that we just did in the last video, which, if you remember, what we did is we solved and modeled the temperature evolution in a bar doing finite differencing, and we, at the very beginning, worked with our heat diffusion equation and simplified it into a much shorter equation that we could work with. Then we went on to solve it numerically. We came up with our TJs, our TJN, and then coded the end. And what we saw there, once we coded it, is that it actually very accurately described the heat evolution into our bar for anything where the R was actually below zero point 0.5. When it got above zero point 0.5, we observed an instability where we saw these huge oscillations to infinity. So what we're going to do right now is sort of explain why we saw that instability occur. And we're going to do that doing something called a von Neumann analysis. So let's get right into that. So first thing I want to start off with is note that this is the actually the equation that we were working with once we simplified our heat diffusion equation from the last problem. So that's our partial of our temperature. We know what our alpha is. We substitute that in for a couple terms and just put alpha there. And then this is our second order partial differential equation of our temperature with x. And one thing we want to note now is that we can also express this equation as this. Tk equals e to the ikx times e to the negative alpha k squared t. And if you don't believe me that we can express it that, I will show you that this is actually going to be the same thing. So if we want to prove that, first we're going to take a partial derivative of this with respect to our time here. So let's take a derivative of our temperature function here with respect to time. And when we do that, we see that we get I squared alpha k squared, all right, all that comes out. And then it's going to be times the same function again, remember, because it's e. So e to ikx, e to the negative alpha, k squared t. All right, so that's for our left-hand side. Now let's solve it for the right-hand side and see what we get. For the right-hand side, we want to take alpha times our second derivative, of our temperature with respect to x. And doing that, we see that we're going to end up with our alpha times, now the second order derivative is just going to be a negative, so I'll move that negative out there, k squared. And once again, it's because it's an e, we keep it and multiply again by that original function, e, I. And our I, of course, here is just an imaginary number, all right? E to the negative alpha k squared t. So our I, we remember, is our square root of -1. It's an imaginary number. So we're going into the imaginary realm here, but that's okay, and we'll prove that a little bit later on. So to show that these two are equal, you might say, well, this has I squared. This is not quite equal to that. Actually, it is, because remember, I squared is going to just be -1. So this is negative alpha k squared e to the I kx e to the negative alpha k squared t equals our negative alpha. Once again, k squared e to the ikx e to the negative alpha k squared t. And we see right here, these two sides are actually equal. So this is a valid way that we can express our temperature. So we can express it as that. Now let's move on to the next part, and I'll show you why we wanted to express it in this different way than last time. Okay, so now we're going to show why we wanted to put temperature in these terms. But before we do that, I said we're going to address why are there imaginary numbers and do we need to worry about them? And so to do that, we want to go back to Euler's formula here and remember that e to the ikx can also just be expressed as the cosine of kx plus I, our imaginary number, sine times the sine of kx. And likewise, e to the negative ikx can just be expressed as cosine kx minus I sine of kx. And so you're saying, okay, big deal. All right, but what does that mean? Well, when we combine these terms, when we combine the two, what we'll end up having is for cosine kx, that's going to be equal just to e ikx plus our I, plus our e to the negative I kx. All right, we're combining them, divided by 2. All right, you see, because we're just combining the two, and then of course divide by 2, and that's what it's going to be. Sine of kx, likewise, is just going to be e to the ikx. Now this time just minus e to the negative ikx over 2. And this is really cool because we see here that we don't need to worry about the imaginary numbers. These are oscillatory functions, and so the i's will take care of themselves. We don't have to worry about it. So we can just express our t in that case then as a summation of terms multiplied by some coefficient. Doing what we're doing here is a Fourier transform multiplied by some coefficient, and it's going to be times our temperature equation there, e to the ikx, e negative alpha, thermal conductivity constant, times time. This our k is once again our thermal conductivity constant. Our t is time. Our alpha is what we described in the last video. I is imaginary, and this is a summation of our terms from k equals negative infinity to infinity. And so we can just express our temperature as some summation of these terms for some k. And this c sub k is just a coefficient that is going to take care of these imaginary numbers because it's symmetric on both sides. This is a Fourier transform. We showed using Euler's formula that this is completely valid and we're not going to have to worry about any imaginary numbers in our temperature, which of course we would have to worry about because you can't have an imaginary temperature. But because it's symmetric, these terms will cancel out. So that's why we want to do it this way, and that's also why we don't need to worry about having any i's in our final answer there. All right, so let's move on to the next part. Okay, so now what we want to do is, since we established we can define our temperature in these terms, we want to, for this von Neumann analysis, substitute that equation, that t, into our original equation that we had from the last video. So to do that, we're going to need to put it in terms that this equation can accept here. So we have our t right here, and we're going to need to put it for a t of j at some value k for all our tj in terms. We'll also need it for our tj plus 1 position at some k for all our tj plus 1 to the in terms. So let's start off with first tj at k. So for that, we're just going to use, we see we're just putting a j position now. So this is going to be e, I, j now, k delta x, right? Because we're just putting it for j, times for the second term, e to the negative alpha, k squared, and now it's for some in time here, n times the delta t, our change in time. Change in time, change in position, times our j, times our n, and that is how we're going to put this first term right here into this equation. Now let's express our t j plus 1 to the k, and let's put that into our equation. So let's do that next. All right, so now let's do it for our tj plus 1k term. All right, so first off, we note that we're doing nothing different in terms of our time here. So this is e to the negative alpha k squared in delta t, because we're not doing anything different for our time. But for this first term from our tjk, we're just adding plus 1 to our j. So this is e to the I j plus 1 k delta x. Right? We're just adding plus 1 plus 1. All right, let's go a little bit further with this, see what else we can do. All right. So we notice that if we can factor out this e, this is plus 1, we can factor out an e here, and I'll show you how. We're going to have our e to the negative alpha k squared and delta t still. Can't do anything with that. But we can factor out this plus 1, and on the outside we'll have e plus 1 ik delta x. Ik delta x. What we'll be left with in our first term here is e I r jk delta x. Jk delta x. And so if we look at this, this should look familiar because it's right up here. E to the negative alpha k squared in delta t. E to the I jk delta x. Yep, we got that. And we're just multiplying it by this. So instead of writing this whole thing, let's just call this t sub j. tj to the k, all right, times ei k delta x. And that'll make it a little bit easier when we go to sub it in. Right. And so that's what that's what this is going to equal right here. All right, our tj plus 1 to k, that's just going to be our tj to the k again times e to the I k delta x this time. All right, so let's go ahead and sub that into our top equation up here. All right, so for some t at position j, at the next time step, we have our tj to the n. Well, we just said that was going to be this, right? That's just going to be e. You know what? Let's just put it in terms of tj to the k. That way we have to sub less in, and we'll just put this in for our tj plus 1. Since we already know what both are, we'll just go ahead and do that. So we'll just call that tj to the k again. Plus sub r. Now we're going to sub in our tj plus 1. Let's just call that tj to k. We have to multiply e times ai. We have to put it to the. We have to multiply our tj to the k times e to the ik delta x, right? Because this is our plus 1 position. Now minus 2 times our tj to the n. Well, we're just going to do the same thing for that. Minus 2 times our tjk. All right. And now what we're left here is our tj minus 1 to the n term. And so there's a way that we can keep it in terms of our tj to the k and just manipulate this a little bit when we go to sub it into that. I'll show you guys how we do that next step. So we notice here that this part is not hard. We're trying to put a term in for our tj minus 1, whereas with plus 1, we just multiplied this. Plus 1, without the j, it's just going to be e to the ik delta x. If it's minus 1, it's that same thing, except this term will be a negative now, just a negative. So what we will be left with is like this, tj to the k, tj to the k, we keep that, except this time it's e to the minus ik delta x. All right. So now we've expressed using this temperature equation we wanted to. We sub that in to each of our terms here on the right side of the equation. And next we're going to show what that means and what boundaries we're going to have for this. So let's do that part now. Quick note before I simplify here. I noticed I wrote k for all of my tj terms here. That's incorrect. These are all supposed to be to the n because we're doing it at some position and time here. So for each one of these, I should have written them all in terms of tj to the n, right? So that's what we're doing when we sub it into this equation. Now we can actually factor out, and I'll show you what we can do. All right, so now that what we're going to do here is now that we have subbed in all of our t's in the appropriate spot, we're going to actually factor out our tj to the n here and simplify this a little. So here's what we're going to do. So our temperature at some position j at a time step at n plus 1 is going to equal, we're factoring out all of our tj's to the n. All right, so that's going to be 1, all right, plus r, just keeping that r here, and that's going to end up simplifying. We're just going to be left with 2 cosine k delta x minus 2. So when we factor out our tj to the n here and simplify it, we're left with this equation here, tj to the n, 1 plus r times our quantity 2 cosine k delta x minus 2. All right, so now what we're ready to do is start defining the domain, the boundaries that we're working within. And we'll see pretty quickly here why our r is limited to being less than our 0.5. So we'll get to that. So what we notice here from this equation that we just found, and in our pursuit of trying to figure out what the bounds of r can be in order to have stability in our plots in our equation, what we notice is that if this part of the equation here is not somehow a fraction either between 1 and negative 1, then this will go to infinity because our tj to the n plus 1 will become our new tj to the n every time we iterate this equation. So even if this was, say, 2, if we're multiplying our TJ to the n at 2, and let's say we're starting out with a temperature of 300, well, 2 times 300 is 600. That's our TJ to the n plus 1. That's our TJ to the n plus 1. Now doing it for the next time step, this 600 is now our new TJ to the n, and we're multiplying it times 2 again, 1200. 2 times 1200 equals 2400. And so you see, we're going to go to infinity here because we're multiplying it by a whole number each time. It's not getting smaller and smaller. It's getting bigger and bigger and bigger. Eventually, we'll be doubling it to the point of infinity. So we notice then that this has to be for stability's sake between 1. This part of the equation has to be between 1 and negative 1. All right. So R1 plus R, 2 cosine k delta x minus 2, that has to be between 1 and negative 1. Doing a little bit of algebra, let's subtract 1 from both sides. Negative 2 R cosine k delta x minus 2 has to be between, we subtracted 1, subtract 1, now between 0 and negative 2. All right. And so let's go ahead and it's supposed to be a 2 here, 2 cosine k delta x. Let's get rid of that 2. Let's just divide both sides by 2 now. All right. So this is going to be negative 1 r cosine k delta x now. Because we divided by 2. Divide this minus 2 by 2, so this is minus 1 now. 0 over 2, that's still going to be 0. All right. So looking at this now, we see that this cosine k delta x is in there. Well, we know that cosine k delta x, that has to be between 1 and negative 1. Why? Because cosine, we remember, is a wave function that's bounded by 1 and negative 1. No matter what it is, it's going to be between 1 and negative 1. All right. Now, if we subtract 1 from that, we subtract 1 that we have here, well, subtract 1 from each bound. Negative 1 minus 1 is just negative 2 cosine k delta x minus 1. 1 minus 1 is 0. So now we have our cosine k delta x minus 1, our cosine k delta x minus 1. We know what this term has to be between negative 2 and 0. So that just leaves our r, okay? So if this is 0, if our cosine k delta x minus 1, if that was 0, that doesn't really tell us anything new. We'd have r times 0. That would be have to be between less than 0 and greater than negative 1. And so that doesn't really help us much. But if it was negative 2, this was if it was 0, if it was negative 2, our cosine k delta x minus 1 turned out to be negative 2, well, then we have our negative 1 less than r times negative 2. So negative 2r less than 0. All right. So what would r have to be between? Well, we'll divide both sides by negative 2. Negative 1 over negative 2 is just 1/2. Since we're dividing by a negative in this inequality, we of course flip this, and we see r has to be less than 1/2, greater than 0. So this right here is it. All right. This is why r has to be less than 1/2. It's so that this term here is going to be some fraction, something between 1 and negative 1. And that way, our TJ to the n plus 1 is not going to go into the infinity. All right, so r has to be less than 1/2, which is great because that's exactly what we observed. That when we had values under 1/2 in our code, it worked out fine. We didn't observe any enormous oscillations to infinity. But when it was 0.55, which is greater than 0.5, greater than 1/2, we're obviously going to get some instability. Because of this, we're going to go to infinity after a number of iterations. So that was the von Neumann analysis. That is why we see that instability in R. So now we're going to do, in our next video, we're going to do something called the Crank-Nicholson. And we're going to show how we can still work with bigger R's but not have to worry about instability. And the way we do that is Craig-Nicholson. But for right now, this is how we found and proved that our R is going to have to be less than a half. Von Neumann analysis. We used Fourier transform, Euler's formula to do that. We took it to the imaginary, but we saw that it wasn't going to be a problem. And using that, we could find out what R was bounded by. So thank you very much, and I'll see you in the next video.